Hey everyone, so I want to continue our discussion about conservation momentum with going over some more of those practice questions. So remember, for all of this, what you're going to do is first draw out what's going on before and after the collision, record the mass and velocity underneath each of the objects, and then you would do P before equals P after, calculate the momentums of each term, add them together, and solve for the unknown variable. If you need a refresher, go back into the previous video. Otherwise, you can begin with this next question. Pause the video, work itself, and we'll go over it in a second. All right. So what we have one object moving to the right, and then we have another object starting at rest, like always. Boom, the collision happens, and we're told that they both stick together and move as one. So we have the initial 1 kilogram moving at zero point 0.5 meters per second. The other object is going to be 1 kilogram and 0 meters per second. And then afterwards, it's 2 kilograms with an unknown speed. We write P before equals P after. We do 1 times zero point 0.5 plus 1 times 0 and set that equal to 2 times x. Clean it up and then solve for x, and we get that the final velocity is going to be 0.25 meters per second. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so this is actually a little bit different from what we've done before. This is a typical explosion question. So despite the fact that it talks about something called recoil speed, it just basically means it wants to know the final speed of the gun. So we start with a gun and a bullet together. They're both initially at rest. So the object is 3.115 kilograms for their combined mass. An explosion happens, and then we have the 3.1 kilogram gun going to the left and the 0.015 kilogram going to the right. Uh, because of the fact that they specifically call this a recoil, is usually referring to the fact that the 3.1 gun is going to be going in the opposite direction as the bullet. But it's also very typical and actually guaranteed that if you have an object that starts at rest, like in this scenario, and it explodes out into two separate objects, they're going to be going off in two different directions. All right, so then we write our masses and velocities on each term: 3.115 and 0, 3.1 and x, and then 0.015 and 500. P before equals P after. We multiply their masses and velocities. 3.115 times 0 equals 3.1x plus 0.015 times 500. Clean it up, solve for x, and we get negative 2.42 meters per second, which just means that it's going to the left, as we already established. Now, one thing to note, because you're most likely going to see a question like this as a multiple choice question, definitely very common. If you're not expected to show work, then one way that you can make this process a lot quicker is realizing that the momentum of this object, which we already said was 3.1 times x, is always going to be equal to the momentum of this object times 500. So you can kind of make your life easier by, instead of writing out this line, just go straight to saying 3.1x equals 0.015 times 500, solve for x, and there you go, you get your final velocity. So again, for a multiple choice question where work does not matter, you can kind of get into the habit of saying, if it's exploding, I know that the momentum of the gun has to equal to the momentum of the bullet. All right. Here's the next question. Pause video, work itself, and we'll go over in a second. All right, so this question's a little bit different because this is actually solving using variable terms. Now, if you ever take physics later on, either in the AP level or over at college, this is going to be very common that you're going to be solving things in variable terms. In fact, it might even pop up on the regents, though it's very rare, and it would probably come up once every 5 or so tests. So again, extremely rare, and it would only come up one time. But basically the idea is we do the same thing that we did before. The only difference is that instead of having numbers, we put variables. So we have the diagram before and after already drawn for us. But what we would do is we'd write the mass, ma, and the velocity v, ma and 0. And then after they collide, they stick together. So the mass is going to be ma plus mb. Like we would have normally added their masses. So I'm just going to write that I'm adding them here. And that the final velocity is going to be x. We do the same thing where we do p before equals p after. We multiply the mass and velocity for each term. So ma times v, mb times 0. And that's going to be equal to ma plus b times x. Clean it up, solve for x by dividing this term over. So again, you wouldn't move the terms one by one. You divide it over as one full object. And your final velocity is going to look really weird, but it's going to be written like this. MAV divided by MA plus MB. Basically, the really nice thing about this is that it gives you a way of getting the final answer regardless of what numbers they give you. So if they told you that this mass was 9 and this was 19 and this number was 2, then what we could do is just plug in 9 for MA, 2 for the V, and 19 for MB, and we can quickly and easily figure out that the final velocity is going to end up being 18 divided by 9 plus 19, so 18 divided by 28, which is going to be 0.64. And then one of the really nice things is that if you accidentally made a mistake and maybe this wasn't 19, this was actually 18, then you could just quickly go back, change the number in a split second, and redo your calculations and see that it's now going to be 0.67. So that's one of the really nice things with solving in variable form algebraically, is that you can get an answer that will work regardless of the scenario. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So what you're going to do here, same thing. We already have the diagram from before the collision, so now we have to draw what happens after. They tell us that they stick together and move to the right, so we're going to combine their mass to be 4, and it's going to move to the right with some unknown speed. Looking at the numbers, we have the 1 and 6, 3 and 0, and then 4 and x. We do our whole showing of work. So p before equals p after. 1 times 6 plus 3 times 0 equals 4 times x. Let's clean it up. We get 6 equals 4x. Tells us that our final velocity for this combined object is going to be 1.5 meters per second. Okay. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. So they bring up this term called inelastic collision. Again, it comes up every now and then. There is a very specific definition, which I'm not going to go into too much detail with because it's related. It is partially related to energy. The main thing that you need to realize is that the term elastic usually refers to things bouncing. I mean, if you just think about elastic is kind of like rubber objects would bounce off each other. Inelastic is the opposite, where the objects are going to stick together. So if you ever see the word completely inelastic, that's just a fancy physicsy way of saying that they stick together. And it kind of implies from this term of it being a composite object, as in they are now combined as into one object. So when we draw it out, we have the two balls being rolling together. So we have velocities going in opposite directions. The collision happens, and then they move in some direction with a combined mass of 0.8. So we record their numbers, 0.5 and 4, 0.3, and again, I have to distinctly make the velocity negative 2, and then 0.8 and x. Now again, this goes back to why it's so important that you draw out the picture. You might get into the habit of just being like, oh, 0.5 and 4, 0.3 and 2, but if you look at this, it doesn't explicitly say directions. It does tell us that they roll towards each other, but they don't say the directions left and right, which, as I've said in previous videos, if you ever see the word left, right, east, west, north, south, when they're specifying directions, usually that means that you have to keep an eye out for it and make whatever they say in the typical negative direction uh, be negative. Here, they don't really tack on a direction, so it'd be very easy to overlook it if you went straight into plugging the numbers. But if you draw it out and you're drawing it out based off of the words that they say, like, oh, they're moving towards each other, so I'll draw the arrows towards, this is the way that you're going to remember, okay, this is going to the left, so I should make that negative. All right. So once again, showing the work, p before equals p after, zero point 0.5 times 4 plus 0.3 times negative 2 equals 0.8x. So we write out the, clean it up, 1.4 equals 0.8x, solve for x, and we get that the final velocity is 1.75 meters per second. So that's the speed that they're going to move with. Here's another question. Pause video, work itself, and we'll go over in a second. All right, so this is another explosion question. Even though I know it's technically there's no explosion, it goes by the same concept. So initially we have a person with their suit, with their equipment, floating at rest in space. Something happens and they end up throwing their equipment. We're going to say that the 1 kilogram tool goes to the left, which means that the astronaut's going to end up going to the right. So recording the numbers, originally it was 91 and 0. The tool, we're told, goes 6 meters per second. That really should be a negative 6. And then 90 kilograms in x for the person. We're trying to figure out their final speed, so p before equals p after. 91 times 0, 1 times negative 6, and 90 times x. Clean it up a bit, and we end up getting that the final velocity of the person is 0.06 meters per second. This makes sense. The person is significantly heavier compared to the tool, so their speed should be significantly slower. One of the reasons why when you shoot out a gun, shoot a gun, and the bullet comes out at an extremely fast speed, but the recoil speed of that gun is typically not that bad compared to the bullet, at least. Oh. All right. And then here is the next question. I think this is the very last question. Pause video, work itself. We'll go over in a second. All right. So for this one, this is your typical conceptual conservation momentum question. It goes back to what I said before with a lot of the force questions. This is going to be a very easy question. It looks like it's super long. It looks like you have to do tons of crazy work, but realistically, what you want to do is kind of skip straight to what it's actually asking about, and you'll find out that you shouldn't have to do any work at all. The question is, the total momentum of this frictionless system is blank, and we have to figure out which one makes the most sense. We know that regardless of what's going on, momentum has to be conserved, which means p before equals p after. The momentum before is always equal to the momentum after. So the only answer that makes sense is C. We know that D can never be an answer. And A and B actually could be answers. So if you wanted to, you could actually do the math and see if it makes sense. In the scenarios before, we had the momentum being 0 before and after. But the main thing is that if it was 0 before the collision, it would also have to be 0 after the collision. So technically, one of these couldn't be right unless the other one was also right. So it's one of those, as a multiple choice, it wouldn't make sense for A and B to also be there together. So the answer is always going to be the same before and after the collision. Obviously, you want to make sure that you don't just always click the same, mainly because they might throw a little curveball and have you comparing the individual momentum, so the momentum of one cart versus the other cart. But typically, if you're seeing a question momentum, you're seeing questions about carts colliding, and they say anything about the momentum before and after, the total momentum, it's always going to be the same before and after. All right. That's pretty much it. So I showed you kind of what to expect as far as free response and as far as multiple choice questions. Um, this like I said is going to be the crux of this unit. So make sure that you go through it, that you understand the momentum, the impulse stuff, but also know this conservation momentum information. If you have any other questions, please feel free to let me know. I actually want to end the video with one last statement, that the idea of this momentum actually ties back to the concept of Newton's third law. So, as we were shown, oh, I guess I'll do it here. As we know, the momentum before equals momentum after. Before the collision, we have the momentum of object 1 initially and the momentum of object 2 initially. And then afterwards, we have momentum object 1 afterwards plus the momentum of object 2 after. If I move this around so I have momentums of objects 1 together, I get momentum of 1I minus P1F, and then I have P2F minus P2I. Now I can actually rewrite this. Final momentum minus initial momentum can be rewritten as delta P2. And then over here, this is this is initial minus final. So that's opposite order. So this is actually would be rewritten as negative delta P1. That the change in momentum of object 2 is equal to the change in momentum of object 1, which makes sense for conservation momentum. That if object 1 decreases in momentum of 5, that decrease had to have gone as an increase to object 2. So far, this kind of makes sense in the idea of momentum always being conserved. Now, if we tie it back to what we said about impulse, we know that the equation for delta P is related to F1 times T. And then over here, I could say the same thing. This is F2 times T. Now, the time that object 1 is in contact with object 2 is the same. So if we drop the T's, we end up with minus F1 equals F2. Now, I don't know if I wrote it out explicitly like this, but this is actually the definition of Newton's third law. For every action, there is an equal and opposite reaction. That the forces will be equal to each other, but will be in different directions based off of their sign. So again, a lot of the things that we talk about in this class will now be able to be tied back to one of Newton's 3 laws. So always keep that in mind when you're doing the problems. Like I said, if you have any other questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.